Hello students, welcome to lecture 21 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on overview of electric metamaterials. Here is the lecture outline. We will have a brief overview of the electric metamaterials, also called as artificial dielectrics. We will look into the electromagnetic properties of stratified metal dielectric composites and discuss about Werner bounds in details. So, here is the overview of electric metamaterials. So, as you understand, these are engineered materials that are made to exhibit specific electric properties. So, when you talk about electric metamaterials, the central concept is that you are going to custom design the electric permittivity, right. So, that is a key parameter that describes the material's electric response or response to an electric field. The main purpose of studying electric metamaterial is that you can create artificial metal dielectric structures which can provide a custom made permittivity value over a particular frequency range. So, if you look back in history, you will see that this particular cup, which is also known as Lycurgus cup, okay, it is a Roman glass artifact which is composed of gold nanoparticles in a ruby host. Okay. So, now this cup has something special. Okay. So, you will see that when you shine light from the outside, you see the cup is green. That means you are seeing the reflected light which appears green. However, if you put the light source inside the cup and you see the transmitted light, the cup appears red. So, there is something interesting happening in this particular cup, and these color properties are basically coming from the mixing rules of metal dielectric materials. People have seen that there are gold nanoparticles in this glass, okay, which has got a ruby host. So, what is happening? There are metal dielectric properties which are giving some peculiar electromagnetic response. Now, if you look at the history of these electric metamaterials, they were mainly studied for radar technology, and over the years the 1940 to 1970s, right, and they were not yet known as electric metamaterials, rather they were referred to as artificial dielectrics. These materials typically consist of periodic metal dielectric units with sub-wavelength metal particles in uniform background medium or host. So, the name artificial dielectrics was prominent, and that was used particularly in microwave technology. That was done to describe and differentiate that these are man-made materials. So, what they used to do, they mimicked the macroscopic analog of natural dielectrics, except their atomic or molecular structure, which in this case will be artificially structured in that form of meta atoms that we have briefly discussed earlier, and that is the principle central to this modern metamaterials. So, Winston Koch, he was a Bell Labs engineer. He basically is considered to be the pioneer of this artificial dielectrics, and he worked on this in 1940s. So, he aimed to develop low loss, lightweight, cost effective radio wave lenses. So, Koch basically proposed several lenses structures consisting of say parallel metallic plates or metallic sphere arrays which are embedded in dielectric matrix. So, his key contributions, okay, or you can say like he pioneered couple of interesting fields in this research of metamaterials, where he used equivalent material properties to describe the electromagnetic response of such composite. Okay. He explored periodic metal dielectric structures with effective refractive indices, both larger and smaller than unity. He also introduced the terms phase delay and phase advance to describe wave behavior, and he was able to draw a clear analogy between artificial and natural crystalline dielectrics. So, among different medium, the rodded medium, okay, that is one of the most important artificial dielectric. So, the name itself tells you it is nothing but a periodically arranged lattice of metallic rods in vacuum or dielectric medium. So, this rodded medium is also known as wire grid or wire mesh. Okay. So, early researchers who basically contributed to the development of this topic include Brown, Rotman and Golden. So, the structure was able to mimic the plasma behavior that of a Drude metal, okay, and the plasma frequency of the composite material can be tuned by varying the geometrical parameters of the wire array, and this is where this artificial dielectric or the artificial metal kinds of concept came in, because in natural materials the plasma frequency is a fixed quantity, you cannot tune it, but here based on the geometrical parameters of the structure you can tune that very fundamental property, okay, and that is where the metamaterial concept came in. So, a similar concept was reinvented by Sir John Pendry from Imperial College London in the 20th century. So, Sir Pendry's work led to the application of this rodded medium into making a left hand metamaterial in the year 2000, and that basically marked the birth of this modern metamaterial research field. Artificial dielectrics, which are working at optical frequencies, were initially impractical due to the limitations in nanofabrication. So, meanwhile, over the years the nanofabrication technology has also gained pace, and a lot of things which were earlier thought of impossible, you can just make them in the clean room facilities these days. Okay. However, initially because the nanofabrication was a big challenge, early researchers were mainly studying microwave frequency artificial dielectrics. However, they adopted the optical terminologies. Something like the refractive index was commonly used to describe the wave behavior in such media, even at radio or microwave frequencies. So, researchers could engineer the magnitude, value and the dispersion in the effective refractive index of this artificial dielectrics in a controlled manner, and this is where the engineering aspect gets into picture. You can actually tune the value, the dispersion based on the physical property of the design, right. So, many microwave studies basically use this phase optical properties when the radio wave behavior is characterized using refractive index, even though they do not particularly operate at the optical frequencies. So, various artificial dielectrics, it can be both periodic or disordered. They basically served as foundation for more complicated metamaterial structures and devices such as negative refractive index materials or optical hyperlenses. Okay. So, we have understood that any metamaterial gets is electric response from the structure, and that is basically very different from its constituent material properties. Okay. So, it does not really depend on the chemical composition, it rather depends on the physical structure of the meta atoms. Thus, all metamaterials, you will see that they are inherently electric metamaterials, whether or not the electric properties are the main focus of this primary study or not. Okay. So, artificial dielectrics are crucial when the desired device requires a gradient in the material property. So, some examples of this kind of structure which has got varying permittivity requirement will include this Lundberg lens, which is a conventional design. So, you can see the blue shading, which is proportional to the refractive index values. This is the cross section of a standard Lundberg lens. Okay. And the other one shows the optical cloak, where you can have an object hidden inside this cloak, and this cloak allows the light waves to bend around the object, so that they can, after passing the object boundary, they again converge in the same way they were before the object. Okay. So, it looks like nothing is here. Okay. So, this cloak material will also have this kind of spatially varying permittivity, right. So, these things you can design based on this artificial dielectrics. So, now let us look into the electromagnetic properties of stratified metal electric composites. Okay. So, that will take us forward to understanding how exactly this artificial dielectrics can be designed. So, in this example, we examine a periodically layered composite of two isotropic materials. So, you can see the materials are basically arranged in parallel manner. There are two different material, one has got permittivity of epsilon 1, another has got epsilon 2. Okay. So, these are basically the bulk permittivity of the two constituent materials, and we can consider the volume fraction of material 1 to be F1, and then the volume fraction of the second material will be F2, which is nothing but 1 minus F1. So, F2 and F1 are related, right. What you can do here, first important thing that you need to keep in mind, that what about the thickness of each layer. The layer thickness is considered to be much smaller than the wavelength of the incident light, and that is when only the system can be considered as a metamaterial, or it will behave like metamaterial, right. So, in this kind of system, there are two principal situations that can be considered. The first one is that the external electric field is parallel to the interface, that is when the electric field is parallel to this interface. Second one will be the one when the electric field is perpendicular to the interface, right. So, you are basically marking those with two different permittivity, epsilon parallel and epsilon perpendicular for the two polarization, right. So, you can see this is marked as epsilon parallel. So, there are two cases when you can have parallel, one along this axis, also along this axis, but this one is the perpendicular one. So, that is called epsilon perpendicular. Now, regardless of the incident wave electric field polarization, the basic constitutive relation holds for each constituent material as well as for the whole composite. So, you can write di equals epsilon I E I. So, E I is basically the electric field, D is basically the displacement field, right. So, now let us look into the case 1. So, case 1 is when the incident field is considered to be parallel to the interface of this layered system. Okay. So, what do you when you apply the boundary condition, it says that the electric field must be continuous across the boundary between the layers, and these are dictated by the Maxwell's equation. So, you can write at the interfaces that E1 equals E2, and that can be taken as EE, that is basically the overall effective medium. So, E here stands for the overall effective medium, right. So, the effective electric flux density dE you can also calculate as a volume weighted average of the two flux densities d1 and d2. So, dE is nothing but the effective electric flux density that you can write as F1 d1 plus F2 d2, right. So, that helps you to find out the effective permittivity also for the parallel polarization, and that can be simply calculated as epsilon parallel equals F1 epsilon 1 plus F2 epsilon 2. Okay. So, how it is coming? So, you basically combining the equations, okay, and that allows you to obtain the effective permittivity, which is epsilon parallel. So, that is basically the effective permittivity along the interface, okay, and that is the case when the electric field is directed along the layers. Now, you move to the second situation where the situation is quite different, because here the electric field is basically polarized perpendicular to the interface. So, we are looking here, right. So, in this case the electric flux dI must be continuous across the boundary between two adjacent layers, okay, due to absence of the surface charges. So, you can simply write d1 equals d2 equals dE. Okay. So, in this case the effective electric field will be calculated as volume weighted average. So, you can write EE, that is the effective electric field will be F1 E1 plus F2 E2. So, from that if you combine the two equations, okay, what you get? You can get they are related, these two will be related by epsilon perpendicular, and then you can calculate epsilon perpendicular as epsilon 1 epsilon 2 divided by f2 epsilon 1 plus f1 epsilon 2. Okay. Now, the effective permittivity of this composite layer can be also derived by the Brugmann's effective medium theory that we have already discussed in one of our previous lectures. You can calculate it as f1 epsilon 1 minus epsilon bg divided by epsilon 1 plus kappa epsilon bg, I will tell you what kappa is, plus epsilon 2 plus f2 times epsilon 2 minus epsilon bg divided by epsilon 2 plus kappa epsilon bg equals 0. Now, here you see this new term, this was not discussed earlier, this kappa, okay, is basically a parameter that represents the screening of the external field by a medium. So, the screening factor can reach its maximum value of infinity when all the boundaries of the composite are parallel to the electric field, and also this kappa can reach a value of 0 if the field is normal to the boundaries. Okay. So, you can simply write it like when kappa equals 0, that means the field is perpendicular to the layers. So, the effective permittivity recovers epsilon perpendicular, and when kappa equals infinity, that is the field is parallel to the layers, that means it will recover epsilon parallel. Okay. Now, these are the two extreme cases that correspond exactly to the two principal orientation of the layered system, as you can see in this figure. Now, you can extend this kind of effective medium approach for this periodically layered system, where more than two materials can be involved. So, say you have more materials, you can find out the parallel permittivity as summation over I fi epsilon I. So, fi will be the volume fraction of material epsilon I or material I, you can say, and the perpendicular permittivity will be written as 1 by epsilon perpendicular will be summation over I fi by epsilon I. Okay. So, that way you can calculate, and you have to just remember that for a multi material layered composite, the sum of all the volume fractions should add up to 1. That means, if you do summation of our fi, that should equal to 1. Now, when the electric field is parallel to the layers, we have seen that the effective permittivity is basically the weighted arithmetic mean of all the constituent permittivities. And on the other hand, if you consider electric field to be perpendicular to the layers, the effective permittivity is basically the weighted harmonic mean of the permittivities, right. So, these are the main differences. Okay. For an arbitrary two phase composite, this permittivity values that you have seen, epsilon parallel and epsilon perpendicular, act as the upper and the lower bound for the effective permittivities. So, these are the two limiting cases, as you can think of. So, these bounds basically correspond to extreme field screening case. So, you can see that when there is full screening, kappa is 0, when there is no screening at all, so kappa becomes infinity. So, that one gives you correspondingly, for kappa equals 0, we have seen you get epsilon perpendicular, and kappa equals infinity will give you epsilon parallel. Now, with that you can discuss and understand that these are basically the bounds, and these bounds are also known as Wiener bounds, which are named after Otto Wiener. In 1912 he discussed about this. So, the Wiener bounds are useful for assessing the range of possible permittivities in a system. So, you got to understand that what range you can within which range you can vary the permittivity based on a particular given system. Okay. So, they can be basically visualized in a complex permittivity plane, where you plot the real part of the permittivity on the horizontal axis and you put the imaginary part on the vertical axis, and each constituent's permittivity like epsilon 1 or epsilon 2 can be plotted as an isolated point on that complex plane, and you can represent each of these as its real part and the imaginary parts, because you can always write any permittivity, the complex permittivity, as epsilon prime plus I epsilon double prime. So, this is the real part, this is the imaginary part. So, let us see how it looks like. So, if you consider the case of two dielectric materials, okay. So, you are basically having titanium, which is -4, okay. So, it is like here, this 5, this is the real axis, okay, real permittivity, this is the imaginary permittivity. So, these are basically the Wiener bounds for the permittivity of a titanium silicon composite at 600 nanometer wavelength. So, how do you plot it? So, let us consider the permittivity of titanium is -4 plus 12I. So, that turns about to this point. So, this -4 and this 12 in the imaginary axis, and then silicon has got 15 plus 0.2I. So, that is here slightly above the real axis. Okay. So, now as you can see that when the filling fraction F of material epsilon 1, okay, that vary. So, you can just say this is basically F1. So, if there is a two material system, it is very easy that if you know F1, F2 is simply 1 minus F1. Okay. So, you can just talk about one material's filling fraction. So, what you see here is that the lower screening bound basically traces a straight line between these two permittivities epsilon 1 and epsilon 2. The higher boundary, so that is basically the lower one is always the parallel one, okay, epsilon parallel. Now, the higher screening bound, which is the epsilon perpendicular, that forms a circular arc, okay. So, the circular arc through epsilon 1 and epsilon 2, and then it comes with the origin, right. So, how do you understand or interpret this graph? So, you can say this is titanium, right. So, when the filling fraction changes from 0 to 1, okay, that means you are basically moving from, say, this lower bound to the upper bound, right. So, as the metal component, which is titanium, the filling fraction is changing from 0 to 1. You can see that the parallel polarization permittivity moves linearly from epsilon 2 to epsilon 1, okay. That is how the solid line is. So, you will actually move along this line. So, here you can consider F equals 0, because you do not have any titanium at all. So, it is purely silicon material. So, you have this permittivity epsilon 2, but then when you keep on increasing the fraction, it will move along this line, and finally, here your F equals 1 and you will have completely titanium material. However, if you look the same thing for perpendicular polarization, you will basically go along this line, okay. So, along with different volume fraction, you are basically moving along this circular arc. Now, what happens for a fixed metal fraction? You can see that the shape dependent effective medium theory will describe a thin curve in this plot, okay, something like this here. So, anything in between epsilon parallel and epsilon perpendicular, okay. So, you are basically moving along this thin curves. So, this thin curve for a given filling fraction basically lies between the two Wiener bounds, okay. So, that actually tells you that these are the two absolute limits beyond which you cannot go. So, layered metal dielectric composites could enable permittivity values that you can see that are unattainable in the bulk materials. So, for F equals 1, you can go in this particular curve, F equals 2, you can go like this. So, this is your lower bound, this is your upper bound, and so on, okay. So, what are the special cases you can consider? You can see that when F1 by F2 becomes equal to minus epsilon 2 by epsilon 1, in that case the parallel permittivity tends to 0, and if F1 by F2 becomes minus epsilon 1 by epsilon 2, in that case the permittivity, the perpendicular one or the upper limit in the permittivity goes to infinity. That means these are the two extremes, okay, that you can always think of, and this is the allowed region of the permittivities that you can obtain from this particular system. Now, if the imaginary part of both epsilon 1 and epsilon 2 are very small, so what will happen? Here it is 12, so it is very high. So, if it is also very small, you will see that their corresponding points on the complex plane will lie very close to the horizontal axis, right. So, as a result, you will see that this particular arc can extend to extremely large values, right, because if this entire line is very close to the horizontal axis. So, that way you can have extreme permittivity values, okay, something like epsilon very close to 0, epsilon near 0 or epsilon infinity, which are also very suitable for photonic nanocircuits at optical frequencies. So, in such nanocircuits, epsilon infinity materials are needed as conducting wires for optical displacement currents, and if you look for epsilon near 0 medium, they can serve as insulators to isolate each functional elements. So, what we understood that this bounds basically tells us the possibilities of a number of metamaterial devices that can be proposed, and people have already demonstrated based on metal dielectric composites this kind of layered structures. By selecting suitable permittivities and filling ratios, it is possible to obtain highly anisotropic material where you can obtain almost 0 parallel permittivity and almost infinity or very large permittivity in the perpendicular direction simultaneously, right. So, this kind of highly anisotropic materials have found applications in super lenses and hyper lenses. We will go into details of these two. So, these are some peculiar applications of metamaterials, and which are very interesting, and with dedicated control of this spatially varying thickness combinations, you will see that the stratified metal dielectric structure can also be used for designing of optical cloaking devices in cylindrical geometry, which people have also demonstrated. So, with that we will conclude here for this lecture. In the next lecture, we will describe the periodic array of metallic wires in more details to tell you how exactly that allows you to tune the permittivity and the plasma frequency. So, if you have got any query regarding this lecture, drop an email to this email address mentioning the course number and the lecture number and the course name on the subject line. Thank you.